The difference between an AI that spins its wheels and one that takes decisive action comes down to this single decision point. You'll see exactly how to implement the routing logic that determines whether your agent should keep processing with tools or deliver a final answer. This is where the flow of your entire agent gets controlled, using just the last message to decide the next step.
From typing import literal. From LangGraph, graph import StateGraph start end. Def should continue state. Messages state literal tool node end. Decide if we should continue the loop or stop, based upon whether the LLM made a tool call. Messages equals state messages. Last message equals messages -1. Hash if the LLM makes a tool call, then perform an action. If last message tool calls, return tool node. Hash otherwise, we stop, reply to the user. Return it.
This demonstrates the conditional routing pattern in stateful workflows, where execution paths dynamically branch based on runtime conditions. The technique creates a decision point that inspects the current state to determine whether to continue processing or terminate, enabling adaptive behavior without hard-coded sequences. What makes this distinctive is its separation of routing logic from node implementations, allowing clean composition of independent components. The pattern works by treating workflow transitions as first-class citizens, where a dedicated routing function evaluates state after each operation. This declarative approach contrasts with imperative loops, as nodes remain unaware of the graph structure while the router handles all control flow decisions. The result is a system where business logic tools model calls, stays decoupled from orchestration logic, making the workflow easier to modify and test. This matters because it solves the problem of rigid execution sequences in multi-step processes. You'd use this when building agents or pipelines where steps may need to repeat, skip, or terminate early based on intermediate results. The trade-off is slightly more upfront design work, but the payoff is maintainable, extensible workflows that can handle complex real-world scenarios without spaghetti code. Let's break it down line by line.
From typing import literal.
Imports literal from typing to create strict string literal types. This ensures the function only returns specific predefined values, preventing invalid return states.
From LangGraph, graph import StateGraph start end.
Import StateGraph for defining graph-based workflows, plus start and end, as special markers used in edge definitions, e.g., add edge start, node to set the entry point, or return end to terminate the workflow. These are core to LangGraph's control flow, as seen in the conditional routing logic of the should continue function.
Def should continue state. Messages state literal tool node end.
This function checks the last message in the state's message history and returns tools if it contains tool calls routing to the tool execution node, otherwise returns end to terminate the workflow. The literal type restricts the return values to these two options, matching the graph's conditional edge definition.
Decide if we should continue the loop or stop, based upon whether the LLM made a tool call.
Docstring explaining the routing logic. This function determines whether to continue processing tool calls or exit the workflow based on the LLM's last message.
Messages equals state messages.
Extracts the message history from the state dictionary. This gives us access to all previous messages in the conversation, which will inspect to determine if the LLM made a tool call.
Last message equals messages -1.
Grabs the most recent message from the conversation history. This is critical because we only care about the LLM's latest response to determine if tool calls were made, not the entire message chain.
Hash if the LLM makes a tool call, then perform an action. If last message tool calls.
This checks if the LLM's last message contains tool calls. It determines whether to route to the tool execution node or end the workflow, implementing the decision logic for the state machine.
Return tool node.
Routes execution to the tool node when the LLM makes a tool call. This conditional return triggers the next step in the workflow graph, handling tool invocation before responding to the user.
Hash otherwise, we stop, reply to the user. Return it.
This is the termination case for the state machine. When no tool calls exist in the last message, we exit the graph and return control to the user, completing the workflow. Conditional flow in LangGraph. The shouldContinue function demonstrates how StateGraph dynamically routes execution based on LLM tool calls, using Python's literal type to enforce strict return values of either tool node or end. The conditional edge logic replaces hard-coded transitions, enabling graphs that adapt to runtime decisions rather than following static paths. Missing a return path from your tool node back to the decision point creates silent dead ends in execution. This pattern transforms linear scripts into stateful, decision-driven workflows with minimal boilerplate.
The edge that connects nothing becomes the path of all return.